All right, so that also puts us in a good position now to be able to differentiate between what a standard deep learning or, for example, neural network is versus what an spiking neural network is going to be. So ANN stands usually for an artificial neural network, but in this particular case, I'm going to be using ANN as an analog neural network as opposed to distinguishing it from a spiking neural network, which is kind of like a digital one. Note, however, when it comes to implementing some of these, they're all possibly going to be implementing in a digital hardware, but the input representation in case of an ANN, I'm representing it as an analog input, and for an SNN, it's going to be basically in terms of spikes. So let's try to understand what the main difference between an ANN and an SNN is going to be. ANN in this particular case, which I'm showing on the left, is a feed-forward neural network where the nodes of these networks are basically showing the neurons or the activation functions, and the outputs of each of those nodes are connected through these wires, which has some weights. As we'll see later on, weights W, and then the inputs are multiplied by these weights, and then we can do some interesting computations that we'll see later on. The inputs, as I said, in case of an ANN or the standard artificial neural networks, are analog inputs and outputs, whereas in case of a spiking neural network, they're going to be in terms of spikes. Now, the difference between the two, as you can also see, is that the timing between the spikes is going to play an important role in case of spiking neural networks, whereas such spiking in case of an ANN does not exist. Good thing about the neuronal activation in case of an ANN, which is ReLU activation, as we said, or could be, for example, tan hyperbolic or sigmoid function, they're differentiable. Now, the differentiability is going to be quite important when it comes to training these neural networks, as we'll see later on. On the other side of it, if you look at the activation function of a spiking neural network, it has what's called a membrane potential. As I mentioned, the membrane potential is stored in a memory, and then the problem with such LIF neuron is that they are not differentiable everywhere. So that can potentially cause a problem when it comes to training these neural networks. The ANNs are trained using standard backpropagation. So does, for example, the standard or SNNs. However, since SNNs we are talking in terms of a membrane potential, which is kind of like a sequential function in a lot of ways, right? Because I can remember the past using the membrane potential. Turns out, in order to now train it, I have to make sure that I do take care of it, the time factor into account. So I can still do backpropagation, but then I have to do backpropagation through time by unrolling this network. And the other problem is that, as I mentioned, that we may not now be able to differentiate the leaky integrate and fire kind of operation that I have the activation function. So I might have to use some sort of an approximation or a surrogate gradient for that. ANN suitable for single shot inference, unsuitable for sequential processing. So people use it for sequential processing, but they cannot effectively capture some of the time sequence data. On the other side of it, of course, the ANNs, SNNs can do that because they have this membrane potential. But I can certainly have time series data or sequential processing that can be done in ANNs by providing a feedback in that network architecture. And such feedbacks now effectively produces a memory in the system. And now RNNs, or recurrent neural networks, are such networks where I can actually provide feedback to that ANN that I showed earlier. And now I can do sequential processing effectively. However, there are several issues associated with that. When it comes to training such RNNs, I have to unroll that in time and during backpropagation. And the second thing is that there's something called the vanishing gradients that's going to come into picture, and that can make training of these RNNs more difficult. Now, RNNs have been, the standard RNNs have been replaced also by what are called LSTMs. And long short-term memory kind of networks. So in this particular case, there are actually nodes in there where I have different kinds of functionality, not only the storage functionality that I have in a SNN, but I also have functionality of forgetting some behaviors. Now, that forget behavior is represented in terms of forgetting can be done using what's called the forget get, which is also shown in these LSTMs. Now, if I now go back to the SNNs are kind of like an LSTM if you think about it. Remember we talked about leak in the leaky integrate and fire kind of operation. So it turns out that the membrane potential decays over time, so it's possible to forget some of those inputs if needed, and that is also quite helpful in kind of SNNs because it can potentially get rid of noise. In terms of the number of parameter counts, in general, and we'll talk about that when we do the system design, we'll see that LSTMs usually have a larger number of parameters than what we'd like to have, than we'd have, for example, in an SNN for sequential operations. So these are the advantages and disadvantages of these different networks that one can potentially think of, and based on that, one can think of the right kind of application. Now, another thing that also turns out to be quite important is that what kind of input should I use for these networks? And as we have seen, in general, for a spiking neural network, I would like to use spike as inputs. Now, if the spikes are generated automatically, then it's good. In a lot of cases, spikes are generated automatically in some sequential operations, like, for example, a DVS camera that we'll talk about later on. Else, if the spikes are not generated, and the spikes and the inputs are in terms of, for example, analog values, then there's a need to think about, making it into sort of a spike domain. And people have done different kinds of representations of those, analog inputs, making them coded them in a rate coding fashion using a Poisson spike trend. However, whenever you're trying to represent it, these inputs in terms of a Poisson spike trend, they're usually associated with a high latency. So for applications where latency is important, it turns out that it may not be a good idea. The second thing is also important is that in general, when it comes to directly having inputs coming in terms of spikes, rather than doing some sort of a spike encoding using rate coding, it turns out that the sparsity in case of rate coding is going to be not so good. That would give us lower efficiency. If I have a lot of sparse inputs, then potentially what one can do is one can do less computations, making sure that whenever there is a zero, you don't do any computation. Whenever there's a spike, you do some computing. It's also possible to use direct input encoding in case of an SNN. So what would be a direct input encoding? One can potentially think of having these analog inputs coming to a spiking neural network. The first layer of the network is certainly going to get your inputs excess in terms of the analog values. Then the first layer of the network then, since it's a spiking network, is going to then potentially generate spikes. So it can be the first layer of the network can be a spike generator, and it turns out if you do that, then you can certainly do much better, would work much better from the in terms of energy efficiency. And of course, at the same time, just because I'm actually doing these spike generators in the first layer of the network, one can potentially show that you have much better latency and enhanced efficiency. So far we talked about different kinds of neuronal activities and the input representations. The activation functions, is it going to be a LIF neuron? Is it going to be a sigmoidal neuron? Is it going to be a tan hyperbolic neuron? And so on. Now, based on that, I would like to then see if I can train my neural networks. So one of the good ways of training neural networks is using backpropagation, and that has been used for a long time and is quite effective. Unfortunately, it takes a good amount of computational effort. So what's backpropagation? So let's try to analyze backpropagation and see what backpropagation does in terms of training. So let's consider a neural network that I'm showing here. The neural networks in this particular case, the neurons are shown in terms of these nodes, and the nodes are connected using weights W1 for the first layer, the set of weights W2 for the next layer, and so on. The activation function represented as A, and the inputs are represented as X. They could be spike-based inputs. They could potentially be analog inputs, as I said. So now, for example, if I try to apply an input to this network, which is in terms of X1s, and propagate the inputs to this network, then what I would get is, at each of those neurons, I actually do an operation which is called, multiply and accumulate. So the weights are multiplied by the inputs, which I'm showing here as Z. Z is equal to some W times W transpose times X, W being a matrix. So W transpose times X. And then after that, the neuronal activation comes into picture. It could be, for example, a ReLU neuron. It could potentially be, for example, a sigmoidal neuron, and so on. And so that activation is represented by A, and A now is given by this function F, which is the activation function. Could be a ReLU, could be sigmoid, tan hyperbolic, or in fact even a leaky integrated fire kind of neuron. And so activation function is given next to it. Now, so now think about it this way, that I show, for example, for training this network, if I show, for example, a cat. The cat is represented in terms of the pixel values of its inputs, and could be an analog value of these pixels. Now I propagate these pixel values through this network, and the output, Y, then is supposed to be, the output neuron, the cat neuron is supposed to be then 1, as an example. But since I started with, for example, random weights, possibly the cat neuron is not going to be equal to 1. So what I really say is that the ground truth is for that cat is 1, whereas what I'm gotten something due to these random weights is a value which is different from 1. So there's what I now define something called an error or a loss, which is given by the difference between what the golden value is supposed to be versus the ground truth is supposed to be versus what I did get. Now that error then, what I do is I try to backpropagate that error through my circuit. And based on the sensitivity of that error with respect to the weights, now I can update the weights. So if the sensitivity is high versus low, I'll have different kinds of updates for the weights. So to that effect, the weights, for example, in the first layer of the network, which is in this particular case, I'm backward propagating, going from Y, the weight delta W, 2 in this particular case for the first layer, is going to be given by the sensitivity of the error with respect to W2. So what I now do is I do a little bit, I take delta E, delta W, and I take the chain rule. Using the chain rule, what I find is that I can represent del E del W by del E del Y del Z, and del Z del W. Right? In fact, if you look at the middle term in there, that's basically the activation differentiation of that activation function, which is shown in red in this particular case. So now this is important. The reason I say that's important is because the differentiation of that activation function is going to play an important role when I backpropagate to update my weights. Now when it comes to, for example, ANNs, the standard networks, what we use is ReLU. And ReLU is differentiable. So that's not a problem. When it comes to, for example, sigmoid, that's differentiable, or tan hyperbolic, that's differentiable, that's not a problem. But when it comes to, if this is a spiking neural network, then F, the activation function, is a leaky integrated fire kind of neuron, as an example, let's say. And unfortunately, that's not differentiable everywhere. So what do we have to do then? I have to make some approximations. And these approximations are what are sometimes called the surrogate gradients. So I have to now come up with the surrogate gradient so that I can backpropagate through my circuit and to be able to actually train these neural networks. And I have to go through this entire process, going from the last layer to the last but one layer and all the way to the input, and so that I can update my weights. Now, so the difference in now training, hopefully is apparent, is the fact that it's the differentiation of these, or differentiability of this activation function turns out to be quite important. ANN doesn't have a problem, SNN does have a problem. Now, on the other side of it, ANN has to deal with a few other things. In general, ANNs are good for, SNNs are good for time series applications, or for example, doing sequential tasks. So that really means that timing between, or the different time steps, or the timing between the spikes is going to be quite important, and learning that is going to make proper sequential learning. So to that effect, in order to do that, I have to not only backpropagate in space, but I also have to backpropagate in time. Okay? And that becomes a lot more complicated, and that's what I'm showing here on the right side of it, that sequential processing over time, both in space and in time, turned out to be important. In other words, in order to do backpropagation through time, what I can potentially do is that I can unroll this network in time and do my backpropagation. Now that's backpropagation. So what's good about backpropagation? It does give me good results. Okay? What's bad about backpropagation? It is slow. And I have to do a huge amount of computations. And not only that, one of the things that I have to do in backpropagation, which is summarized on the left side of it, shows that I first have to do forward propagation, figure out the errors, and then backpropagate. And during backpropagation, I have to calculate the gradients. And not only the gradients, the weight updates require that exact knowledge of the weights of all layers during backpropagation. So the question then becomes, this is expensive, certainly does a good job, but can I do better? Now, such techniques backpropagation, as you've seen, can be applicable to spiking neural networks, or can be applicable to the standard deep learning networks. But can I do better? Can I do some local learning? If I can do some local learning, in that case, I can actually reduce the amount of computations. So to that effect, research has proposed what's called direct feedback alignment. So what is direct feedback alignment? So as you can see in this particular case, I forward propagate to the circuit, to my network, and I get the error at the output, just like in the previous case. But now, rather than propagating the error through every layer, I provide that error signal to all the layers simultaneously. Now this error signal now goes through what's called direct feedback, the random feedback connection matrix. And that random feedback matrix connection, and it can be random, basically determines what my weight updates are going to be. So in other words, in this particular case, I don't go through all the layers. I provide, in this particular case, the error signal directly to each of those layers, and they go through that random matrix, which is called the random feedback matrix in this particular case. And my weight update in this particular case, again, remember that B matrix, which is the random feedback matrix, has to have the right kind of XY, the length and the width of that matrix has to be proper so that it matches with each of the layers. That's important. So now my delta W in this particular case, as opposed to the previous case on the left side, I'm showing that there's a W2 term comes on the right side of it. But in this particular case, it's going to be going through that random feedback matrix B, the B transpose, and that's it. So if I do that, it turns out, in contrast to backpropagation, DFA does not suffer from weight transport problem that I have in the previous case, and instead using a random connection. The complexity of the DFA, without going into the details of it, is order of Cn, where C is the number of classes and N is the number of neurons. And in contrast to BP, which is a backpropagation, it's about order n squared. So that's a big advantage. However, the only problem is that even though it can be applicable to a large class of circuits, it does not scale very well. Okay? So the problem with DFA doesn't scale very well for deep networks. It actually works well for smaller networks. So the next question, of course, is then, can I do better? Can I use bioplausibility to make my local learning a little bit better? So to that effect, one can also do synaptic updates. Okay, this is the same slides. I'm going to skip that. So to that effect, the synaptic updates can also be done using another local learning scheme, which is more inspired from what has been observed in the brain. So it turns out that synchronous firing of neuronal ensembles have been observed in the brain. So as an example, if I show, for example, a cat, a certain set of neurons would fire at the same time. On the other side of it, if I now show a dog, a different set of neurons, a set of ensembles would fire. So the neuronal ensembles are, neuroscience claims are fundamental to learning and memory formation. And they encode specific information through their coordinated activity. And their synchronous activity strengthens synaptic connections via different kinds of learning mechanisms. I haven't talked about spike timing dependent plasticity, which I'll do in just a minute, but those can effectively be used along with such synchronous firing of neurons. So the question is, can I effectively use that in my training, in my local learning? So to that effect, we recently developed what's called the local learning rule, which is inspired by synchronization. So the basic idea in this has, again, similar to direct feedback alignment, except there are subtle differences. So what are the differences? Here I'm showing a network on the right side. As you can see, layer 1 through layer L, and the output of it is represented again by H, and the intermediate nodes all by H. Now, if you look carefully again, each of the layers are associated with a matrix, just like in the previous case when you have a direct feedback connection. Each of those are now associated with, for example, a matrix called a periodic, using fixed periodic basis vectors. Now, interestingly, this matrix is an H by the number of classes that we have, this matrix. So in other words, in this particular case, what I have is each matrix has an output, which basically says, what class it is. So at each layer, I actually have a class associated with the input that I show. So I do not propagate the error signal to all of the internal layers as we did in direct feedback connection. But in this particular case, I actually have output for each of those classes in every layer. And I just want to make sure that I do my training in such a way that I actually have the same kind of periodic basis vector. I map it to that particular periodic vector, and I have that same synchronicity for each of those classes. So to that effect, what I in this particular case do is look at the layer right below the L that I'm showing here. You have this new matrix B, which is basically this fixed periodic basis vector matrix, and we have it per class. And as I show an input, a primary input with random weights, what I now do is I basically figure out, hey, the loss at that particular point. And then the blue line, which is shown at the bottom below, 1 and 2, basically propagates through that feedback matrix to align the synchronicity that I'd like to have, and then I get a loss, right? If I don't have the right kind of synchronicity, then I'm going to have the loss, and based on that loss, I now go through and update the weights for that particular layer. Okay. Now, interestingly enough, and this has a lot lower complexity than backpropagation. And what I also wanted to show you here is that as an example, we applied it to a larger scale network, and input class 1 in this particular case, a dog, and then showing basically the layer 4. How does that representation of the dog looks like at that particular layer in layer 4? And on the right side of it, what we are plotting is basically the fixed periodic basis vector and the frequency versus the mapping that it did after learning. As you can see, there's a reasonably good amount of synchronicity between the learning that I did versus what I actually wanted it for that particular class. So one can apply to larger scale circuits and larger scale data sets and networks. And turns out on CFAR10, we observed comparable accuracy to, for example, BP, the backpropagation, which is the standard one can potentially think of, with about 150x reduction in the number of MAC operations and 2x reduction in memory requirement. That's quite a bit of improvement, but remember that at each of those layers, then I have to really think about mapping it to a particular periodic basis vector. So CFAR10 certainly works well, tiny ImageNet certainly works well, but if you have really large number of classes, 4,000, 5,000, 6,000 classes, then this matrix becomes really large, and that can be a little more problematic to do. All right. Still going with local learning, but one can potentially use local learning in a spiking environment. But again, whatever I've talked about so far can also be used in spiking, but there are some other specialized local learning suitable for standard spiking neural networks, and people have observed that in the hippocampus of brain. Hippocampus of rats. So to that effect, I'm going to talk about what's called STDP, or spike timing dependent plasticity based learning. Again, not applicable to very large scale circuits, requires some modification, and some modifications can lead to learning in a larger scale, but still not comparable to what can be done, for example, to what backpropagation does. All right, so again on the left side of it showing the standard neuronal activity, and on the right side of it see how local learning like STDP can be used. So I have 3 neurons in this particular case, I1, I2, I3, and an output neuron O1. The weights as an example could be W1, W2, and W3 as an example. And let's say that I have inputs that are coming in to these 2 neurons, I1 and I3. I2 does not have any input. And due to this inputs coming in, the output of neuron O output spikes, which is shown in red. So obviously, by looking at this, you say that the output spiking really happened mainly because of the input activity at I3. I1 also played a role, but I2 did not play any role. So why not update my weights based on the timing difference between the input activity and the output spiking activity? So in other words, I'm going to update the weights for neuron I3 more than the synaptic updates can be more than what I do for I1, and I'm not going to do anything for I2. But in some cases, I might actually also penalize I2. So to that effect, the timing, the difference between the two basically tells you how much of an output, change in delta W, the weight that I should do. Now it turns out, so the new delta, and the new weight is going to be the old weight plus some delta, which is a function of timing difference between the output spike and the input. Now it turns out it's also possible that you might get a spike in I2 later than the spiking activity that happened in the output neuron. So in that case, I actually end up penalizing that weight. So rather than doing synaptic updates the way we did, in case of causality, I actually do, for example, weight updates in a different direction. All right. So that's one way of doing learning, and this is a completely localized learning. However, as I said, such localized learning is applicable again to smaller scale circuits. So maybe the idea is to then combine such local learning with some global learning to be able to actually do effective learning of these larger scale neural networks. All right. So far we have talked about neurons, and we have talked about weight updates and learning. And the next set of things that we're going to be looking at is, since we have talked about learning, neuronal activations, and so on, can I use it for object detection and recognition?